Hello everyone, this is Tim Bergsma from Metrum Research Group here in Terriffill, Connecticut. I'll be your lecturer for MI205 today, and also I'll be back on Friday to cover any uncompleted material from Chapter 3 and to provide some extra laboratory time and to answer your questions. While we go through this material today, please do make use of the question mechanism in the meeting software. I have the questions pane open on my other desktop, so I'm watching periodically to see what questions you're asking. Someone has asked if we have new material for this week. I'm not posting any documents this week. You should have a PDF of the course book, which I will be following closely. And the chapter I'm following is Chapter 3. I'll pop that up on screen real quick for you and find the top of the chapter here. Basic function writing. We have several objectives to go through this week, and we'll probably deal with just more than half of those today. We'll see how fast things go and how many questions you have, but certainly we'll have time by the end of Friday to wrap up all of the objectives here. Someone is saying we do not have Chapter 3. Apologies for that. I'll make sure that we upload a copy of the book that will include Chapter 3. That's very interesting. I'll coordinate with the other authors and figure out how we're releasing the chapters. I know Chapter 3 exists in some versions. What I could do right now is zip over to the course website and just take care of this immediately and add that chapter up there. You know what, that's going to be a little complicated. Let me do that after class. Sometime shortly after the end of the class, my version of the book will be online or something very similar, so you'll have my Chapter 3 to look at. When I get to the exercise portion of the class, I'll show you my copy on screen so that you have a visual idea of what's coming. All right then, so on to today's main topic, and that is function writing. Just a comment about functions in R. Functions are central to the way R works. Obviously there's a lot of things that you can do on the command line that may not seem to involve functions, but really underneath they all do. Functions in R are objects, just like data structures are. You've used a lot of them already in the plotting work you've done earlier, etc. The real power of R is revealed when you start to write your own functions. And that's one of the goals of this chapter, is to get you writing your own functions in R. It's the fundamental way of encapsulating basic procedures and methods that you develop. Without the ability to encapsulate those procedures, you're stuck having to repeat them constantly, with the risk that you'll make tiny errors or big errors in one variant or another of your copied work. It also creates for very bulky and complex code that's hard to read. If you can capture your algorithms as well-defined functions, you can hide them in another file or in a package somewhere and call them explicitly as needed. And that's what we want you to be doing today. So with that, let's start off with a very simple example of a function definition. This one you'll see in the book later when you get the revised edition. We're just going to pick a word. We'll call it opposite, because that describes what my function is going to do. And we define it using the R keyword, function. This says that we want to create an object and assign it the value of a function. We'll create an argument for this function, x. Some of the syntax here looks a lot like standard mathematical syntax. And oops, that didn't quite work out right. You know what I really want to do is do this in a file that I can source. So let's do that right now. Open a file, new R script. Much better. Try that again. Now I include a curly brace here because that's a standard way of collecting all the content of your function. That is the function body. And here I'm going to have a very simple function body that simply returns the opposite, numerical opposite of x. And my function is defined. Quick rundown of the various parts of this function. Opposite is its name. This part of the function is called the declaration. Everything from the open curly to end curly is the function body. And here we have an explicit return value. Now let's go through this again a bit more slowly. Function name. This happens to be a named function. Functions don't really need names. Actually, sometimes we create anonymous functions. Those are simply functions without names. So for example, I could just highlight this part of the function and I could source it. I'm going to use keystrokes on my machine that actually run this, and you see it pop up in the box down below. Mention in the chat if that's too small or if you need it repositioned on the screen. And R says, hey, no problem, we have a function, it has one argument called x, it has a return value, great. Unfortunate thing here is that an anonymous function is perfectly useless in this global context. It could be useful, however, as an argument itself to some other function. We'll see later in the course that many functions require other functions as arguments. That's where anonymous functions have their power. Right now, we'll be much better off if we explicitly name our functions. So we'll go back and source this whole thing. Down to the command line, we see now that we have a function with a name. And we can... Actually, what I'm going to do here is I'm going to use the ls function to show you that it now exists in my global environment. ls is a listing function, shows me everything that's sitting around global environment, and I say I have one thing, it's called opposite. Actually, I'm going to try something else that I didn't plan to do and see what kind of a thing opposite is. I'm going to check its class. Turns out it's a function. No surprises there, but it's a useful technique if you've got a lot of things sitting around and you don't remember what you did. So opposite exists, it's a named function, and it has an argument list. Its argument list is really short. Right now it's just one argument, x. It's worth noting that functions don't need to have any argument at all. In this case we have one, but we could have said something like hello is a function of nothing at all. We could just say no args and just say print hello. Let's try that. And then if we actually call the function, the way we call a function, as you know, is simply by typing its name and then supplying whatever arguments are required, even if there are none. If no arguments are required, we just put empty parentheses behind the function name, and the function does what it's supposed to do. If, however, we tried something like that with opposite, empty curlies, we should get an error, and we do. It says, hey, when we got around to evaluating x, well, there wasn't any x, so don't know what to do anymore. That's an error. Okay, obviously for opposite, it has a longer formal argument list, so it needs more actual arguments. Important distinction there. Formal arguments are the arguments you name when you write the function, when you define it. Actual arguments are the arguments you pass it when you choose to execute it. So here we'll take the opposite of 5, for instance, and we get a result of -5. Pretty trivial operation here, but useful for illustrating the basic parts and operations of functions. Of course, as you know, R is inherently vectorized, so we could have done the same thing with an argument that had some length to it, like this. And 1:5 evaluates to a vector of length 5, and the function opposite gives us the opposites of all of those. I have a request here to enlarge my RStudio screen. I can make the real estate larger, but I think what you really wanted was the font to be larger. I'm not sure how I do that. Well, you all have versions of RStudio. I'm a little new to this one. I usually work with the desktop version. If you know how to make the font larger in the console display, please let me know right now by chatting something in the question box. Otherwise, I'm just going to quickly look through my tools. Let's see, what does tools give me? No, options are editing, appearance, panel layout, cancel. Now I'm not seeing how to do that right now. So with apologies, we're going to have to make do with this font size now until I discover it after class, until someone suggests it. I have another question. Print hello does not need to include semicolons after function. Very good point, and I was coming to that, and I'll deal with that right now. When I wrote the function body for hello, there were no curly braces. You'll note right here in this part of the console. If you only have a single statement as your function body, then you don't need curly braces. I'm going to go ahead and move hello up here so we can define it together. You could have written this, but that would be exactly the same as the other version we had before. They give the same result. So in contrast, we could have taken opposite and written it as what I call a one-liner. That's a function declaration with no curly braces. That works for one-line functions. If you wanted to do something really fancy all in one line, you could actually get away, I think, with a semicolon, like print hello, semicolon, print world. Let's try that. Haven't actually tried that before. And it gives a surprising result. It looks like it's only, well, that makes perfect sense. So that's a legal definition, but it does not give us what we expect, for reasons I will explain in just a moment. Meanwhile, we pause briefly because someone's given me a suggestion. I think you can change font size under appearance. Option, appearance, tools, appearance. Okay. Tools, options, appearance, font size. Let's run it up to, say, 14. Whoa. Hey, I like that. Hope that's working for you. If not, let me know and we'll bump it up further. But I can still see everything I need on screen. You can see the results. Let's scroll down there a little bit. Very good. So we were talking about whether or not you need curly braces. Not for a one-liner, but watch out. This particular version of hello fails because of the principle of return value. Now, let me state clearly that every function has exactly one return value. That's a rigorous rule enforced throughout of R. You always will have a return value, and there will always be only one. In the function we wrote initially, we made the return value explicit by using the reserved function return, or it might be actually a keyword rather than a function. But return says, hey, this is what we want to send back to the user. One thing, the opposite of X. If we had neglected to say the return value, well, you know what? I'm going to go ZZ back here. Control Z back. I'm going to leave that like that. I'm going to make a new version of opposite. And this time I'm going to write it as well, we'll leave it as curly braced. But just to show you exactly what's going on, it's possible not to say return. If you don't have the return statement in your function, then the last expression evaluated is your return value. I'll repeat that one more time because it's so important. The last expression evaluated is your return value. Very often I find myself writing anonymous functions and they do all the right things, but I forget to issue a return value, and then I'm getting a surprise because I didn't attend carefully to what was the last thing evaluated. Sometimes the last thing evaluated in my function body is just some assignment which returns true by accident, and then I don't get what I expected. So let's define opposite this way, and we're going to show again that it works. It does. Just simply because R went through the list of lines of code here and it only found one, and that was the last one, so it evaluated it. Now let's look at our function definition for hello again, and I just ran it. You see that there are two expressions to evaluate, print hello and print world. Since there are two, only the last one got evaluated. We hadn't said anything else. If we really wanted to print hello world, we'd be better off writing something like this. How about return is paste hello and world. There are other ways you could have done this. And then we could say return and then name the object we've just created. That works. Now we get the result I had intended above. No arguments, we evaluate hello, and we get the full statement. Okay, so just to recap, we know the various parts of a function. We know the difference between an anonymous function and a named function. We know that every function has an argument list which may be empty, and it has a return value which may be implicit, in which case it's just the last one. So I think now we're ready to consider, actually we also considered a function definition that has an extended body, that is several lines of code as its function body. Before we move on, I'm just going to give you one more example of something with an extended function body, just to give a greater feel for the art of defining functions. In this example, I need to write a function that removes all the missing values from a vector. So for example, I'm going to create a vector that has a missing value. And I'm going to assign it to some object name. I'll source that. We can display it by typing its name. Okay, just a simple vector with one missing. Now, let's write a function. We'll call it NA_drop. It's good to take some time to think about your function names. And I'll just say this as an aside, because if you name functions hastily, they might not describe what you're really trying to do. Also, you may accidentally use names that have already been used by someone else. Try to pick names that are descriptive, that are easy to type, and that are not in conflict with commonly used functions. The only way you're going to know what's commonly used is to gain experience with R. If it's something that's in base R, you'll know it right away, because you'll either get some sort of warning or you'll get crazy results from other functions. For example, we would not want to call our function this, because this function already exists. We used it earlier. And if we gave a function definition to ls, we would actually be redefining the base function ls, which would no longer work as intended. So we're going to call it NA drop because this function drops NAs. And we'll explicitly say that it is a function here, and we'll give it an argument of x. And this is going to be a complex function, so we'll make some curly braces here. First thing I'm going to do is find out which of my values of my function are NA. The language already has a function to check for NAs, and what it returns is a list, a true-false list, as long as your argument. So that means bad is going to be for missings. It's going to be false, true, false. I can use that to subset x, and I'll store the result. I'll define my good values as being those from x that are not bad. And since bad is illogical, then the exclamation point operator quickly reverses the logic and gives me the not NAs as a true-false vector. When I use that to subset x, I actually get a return value that is shorter than x was. That's the default behavior when you pass a logical as a subset operator. Now let's go ahead and explicitly return good as the result of this function. We could have also just written the word good and been fine with that. We're going to source this with a couple of keystrokes. I believe one of these buttons up here also submits those to the command line. I never use those buttons, I just use the keystrokes. On my computer it's command return. And let's try it out. NA drop my missings. And you see the NA is gone. So this is the result we had intended. If we had lots of time, we would try all kinds of other test cases to see if there's some case we had not anticipated that breaks our function. We'll get into more of that in some other chapter, debugging functions and so forth. Right now, we have a good idea of how this works. We've seen 2, 3, or 4 examples of how to write a function in R. I'm not seeing any questions in the question box. So I'm going to give you a quick preview of the exercises that you'll be working on, hopefully before Friday. So this is in the book, which I'll post later. This is chapter 3, exercises 331. At this point in the coursework, I would have you create and save a file to store the functions that you're going to write below. Actually, you know what? I didn't fully demonstrate that. So please excuse me, give me a little time out here. We've created a file, but we haven't saved it. So let's go ahead and do file, save as. We're in our home directory. I'll call it functions.r. You see it appear over here. Right now, just for demonstration purposes, I'll say ls. I'll show all these functions and data that we've defined. I'm going to also do something called remove. And I'm going to remove everything that can be listed. rm list equals ls. And you see the workspace change up here. All my functions have been taken away. Now if I say ls, I get nothing as expected. So what I need to say instead is source, and then I name a file. Since it's in the same directory, I can just give an unqualified path. I'll just give the name of the file. And when you source some functions, perhaps you've seen this earlier, then you get the result that those functions are loaded back into your environment. You see them appear up here, and you could also say ls and see that they're back. Okay, maybe you knew that already. It's good to go over it. for recording purposes to be thorough. Now you can do part 1 or item 1 from the homework exercises. You can also write a function that returns the first element of its argument. So you saw that I dropped NAs in one of my functions. Now you're going to be dropping everything except the first element. That's a subset operation. Put a question on the course site if you don't know how to do the subset operation. Using source, you saw a demonstration of that just now, so you can do that to load your function definitions. Make sure it works, because that's one of the whole points of writing function definitions is to get those functions out of the way. Truly out of the way means you've written them a long time ago and they're just in a file now, and in that case you'll want to source them. Then, just for a trivial test case, you'll want to write a function that squares its argument. And you can do that with standard R syntax. Again, ask a question if squaring arguments is new to you, or if powers are new to you. Might not be after the next part of the lecture. And here's a brain teaser for you. Number 5 asks you to rewrite NA drop, which will be in the chapter above, as a single expression. In other words, I'm saying, yeah, you can write it this way, but you can also write it as a one-liner that has no curly braces. So that's a little bit more of an intellectual challenge, hopefully not too bad. You might be able to find a way to write this all as a single expression so that the last thing returned is the only thing that there is to return. Okay, I see that we are losing audio. Cannot hear you. Sorry for that. You know what? I'm going to give you a 2-minute break while we check with our audio engineer, because I am adjusting all the controls I can on this end, and that may or may not be helping. So see you again in 2 minutes. That will be 1:30 on my clock, and we'll pick up where we left off. If you need to do something with your free time, you can get started on your exercises. I'll be right back. Okay, my audio engineer is telling me that there's no problem at the recording end of this presentation, so you probably have a bad connection on your end, and you may want to log out and log back in. That sometimes fixes it. Other than that, I don't have much to suggest. Let me know if you're able to rectify that situation. Okay, then I'm going to continue right now with the lecture part of the course. And I'm going to do that with a side topic. And the side topic is this: operators. It turns out that operators really are just functions in the R language. And that's convenient because they often are functions that require multiple arguments, which will be next on our list of things to look at. So given a simple case where we say 2 plus 3, that looks like a language construct in R, and it evaluates as you'd predict. Really what's happening is that plus is an operation, and the R parser evaluates this and says, hey, you know what, really that's just a binary operator which has a function definition. And we can see exactly what that function definition is by placing the operator in backticks. Now on my keyboard, the backtick character is up there under the tilde next to the 1. And if we do that, then we see we've displayed the function body, or in this case, the function declaration of plus. Unfortunately, it's not very informative because it turns out that addition is a primitive function in R. That means it's actually defined in the C language, and the code is hidden from our view. All it is a primitive plus operation. But it is a function, we've learned that much, and that means we can do some weird and wild things that you'd never try during daily operations, but just to prove to you how really much a function it is, we'll try a very unconventional invocation of addition. Instead of saying 2 plus 3, we'll say plus, and supply the arguments explicitly as though we were talking to a regular function. And you see we get the exact same result. It looks a little strange at first, but it all follows from the fact that operators are really just functions. Now, the addition function has a different style of argument list, different set of formal arguments than what we've been using already, for the simple reason that there's more than one. For addition, it doesn't really matter so much whether we're talking about 2 plus 3 or 3 plus 2. The same thing happens because of the commutative property of addition. But you see in the function definition, those are different. It's actually E1 and E2 that are being operated upon in primitive binary operators. Well, we're going to start writing functions that have multiple arguments. And even though this is defined in R already, we're going to write our own power function. We'll call it pow for lack of something more interesting. And we're going to say it's a function of two things, x and y. And we'll be distinguishing them in the function body. This can be written as a one-liner. I don't know why you'd ever do this except for demonstration, because we already have this syntax in R. In fact, I think you have your choice. We could also use this syntax in R, x to the y, and that's the definition of power. Let's go ahead and submit that to the command line, and now we can do really amazing things like pow of 2 and 3, which you'd expect, and pow of 3 and 2, which proves that power operations are not commutative. Now, it's worth noting here that there are different ways to invoke a function. Here we have not bothered to name the arguments. And I might be getting ahead of myself because I think I deal with this explicitly later in this chapter or the next. But we'll throw it in here because it's an excellent time to see this. We could have said this, and watch closely, pow y equals 3 and x equals 2. So now R doesn't care what order you give the function arguments if you name them explicitly. If you don't bother to name your functions, R has to guess, and that's what gave the 9 instead of the 8. In this case, with y and x named explicitly, even though they're given in reverse order, we still get back the previously intended result. In fact, one could have said this, y equals 3, and by now R has enough information that it can guess why we're passing 2, and we don't even have to name that one. We still get 8. There's actually a distinct set of rules that R goes through when it evaluates arguments. First, it'll strip out all the named arguments, and then it'll start matching the unnamed arguments in order of the formals that are still remaining. Okay, you didn't have to follow all that. It's a mouthful. We'll get to it later. I just thought you should see this now because it may be helpful to you at some point. With that, I'm going to pop up on screen a couple of other practice exercises that you can work on before Friday. And let's review those quickly to see if you have all the tools you need to do them. From section 341 in the book, we have an assignment to write a function that concatenates a protocol number and a subject ID separated by a hyphen. Now in pharmacokinetics you have problems like this all the time. You're preparing a data set and you have data from clinical or data from a sponsor that needs to be massaged, as it will, or reformatted. They gave you a column for protocol and a column for ID, but maybe you're combining two protocols and IDs are not unique across protocols. So to get a unique subject identifier, say for a modeling exercise, you need to combine those two columns. You saw me use the paste function earlier for hello world. That would probably work here. I'll let you look at the help for that, which you could find right from the command line. That pulls it up in help if you are not familiar with that, or you may have seen it in a previous lecture, so no big issue there. Number 2 says write a function that normalizes weight by some typical value, rounding the result to 3 significant figures. The point here is to have something a little more complicated that probably takes more than one line of code, or at least it might at first, even though it could be reduced to a single expression after a while. I think you probably have enough to do that. You can always ask me a question offline if that presents some sort of a challenge. Number 3 says write a function that normalizes x by its median. R has a function called median, you can use that, and rounds the result to n decimal places. R also has a function called round, which you may have known, and you can find its help using the standard mechanisms, and there's a way to supply the number of decimal places that you're interested in. Okay. So let's continue then and talk about some other topics. We already talked a bit about default argument values. For example, just to review, if you said pow 2, 3, you get a result. But if you said pow without any arguments at all, you would get an error. You knew that. And I correct myself, we didn't actually talk about default argument values. We talked about regularly defined argument values and supplying them in different orders. Now we are going to talk about defaults. You know that R has a mechanism for, or a list of rules for matching supplied arguments, actual arguments, against the formals that were defined for the function. Those rules include a mechanism to handle arguments that have default values. So, for example, in this case, we could have set a default for y. We could have said that x is whatever the user wants, and y could be whatever the user wants. But if the user doesn't supply it, it's 2. That would be a default argument. And I see I have another question. And someone says, okay, we would expect to get something before the lecture. Thanks. Yeah, you'll have everything you need to do these problems before this lecture is over. Okay, now if we redefine POW to include this, then we have options that go beyond what we previously had. We could say POW of, say, 3 and 2, which gives us 9, but the exact same result would be achieved by taking the power of 3, which is also 9. And here we did not get an error. Even though we only supplied a value for x, we did not get an error because y has a default. Now, the concept of default argument values may be familiar to you from other languages, so I won't belabor it. But the point is that you can adjust your argument list to include defaults for arguments so that if there's a reasonable value to guess for any particular argument, the user doesn't need to supply it. Now that's very important because sometimes the functions you write will take lots and lots of arguments, and it's painful to make the user go through and supply 5, 10, or 15 arguments when most of them are obvious, like what the working directory should be, or something like that, or a stub file name, or an output file format or something. Note that we do need to be careful here. If we said POW y, let's see, how could you say something? If you said y equals something else, y equals 3, and didn't supply the x value, R would catch the error. Okay, because now even though you supplied a value for y, that's called overriding the default, you haven't supplied an x. You would need to do something more complete to get the regular function evaluation. Does that make sense? I feel I wasn't terribly articulate on that particular example. If you still have a question about that, I can go into more detail. Otherwise, I'm inclined to get moving for more advanced topics. Okay, so not seeing any more, we're going to move on just a little bit. And now I'm going to write you another function that has a more interesting default. And this function is going to determine the area of a rectangle. And the area of our rectangle is going to be a function of width, and of course it's going to be the function of height. And in this case, we're going to let the height have a default. Now, it's good to supply, as I said, a default for an argument anytime that there might be a best choice or an obvious choice or some interesting choice that people would immediately recognize. And the classic special case of a rectangle is, of course, a square. And a square is just those rectangles that have height equal to the width. And here we borrow a special property of the R language that your defaults for arguments can themselves be other arguments. They can even be functions of other arguments that are defined elsewhere in this list. They don't even need to be defined in a particular position in the argument list. In other words, we could define height equals width first and then define width if we cared to. Normally, I let the later depend on the former, so this works for me. And we'll go ahead and calculate this as a one-liner where our function is width times height. Let's go ahead and source that and then give a simple demonstration. If we take the area of a rectangle that is 3 by 4, and then I'm sorry, that didn't work for some reason. Oh, I didn't give the whole, sorry, rect area. Here we go. 3 by 4, we get 12. But if we just took rect area of 3, then our function assumes we're talking about a square. It doesn't bother asking us for the height and goes ahead and assumes height equals width, aspect ratio of 1, and we get the expected result. Any questions about that? Seeing none, I'm going to introduce another very important concept in the writing of functions. And you see it over on the right-hand side of the page in the definition of paste. In fact, we could put the definition of paste right on screen here if we just type its name. Again, to get the function declaration, we just type the name without the curly braces, and then you see its arguments. Oh, by the way, another very useful way to view arguments is with the args function. Maybe that was mentioned earlier or later in the book. But we could say args of paste and see just what we need to do if we're invoking the paste function. You see the ... Now the ellipses are a special argument that make your function flexible. And the nature of the flexibility is this. If the formal arguments of a function include ellipses, then the function will accept unrecognized arguments. So let's go back to our rect area example. And let's suppose we were confusing, well, let's just go ahead and do all the formals here. Let's compute the area of a rectangle where width equals 3 and height equals 4. That's no surprise. I recall the command with my up arrow. And let's suppose we were confusing this function with something that computes volume. And we went ahead and said depth equals 2. Now this should generate an error. It's a very useful error because you generally don't want people invoking your function with arguments that you never knew about. And in fact, you don't want yourself to actually invoke your own functions with arguments that you had not intended to use. That would really be an argument for something called volume, not for something called area. So not appropriate here. We'll see an example where it might be more appropriate in just a second. What we could have done, however, was redefine rect area to include the ellipses. Now, I'm not necessarily recommending this for use as an area calculator, as a volume calculator, but it could be useful in other contexts. We'll go ahead and leave a default for height here, and let's put the ellipses in. Oops, didn't mean to do that. Leave that up there, and we'll source this. I'm missing something here. I don't know, I'm getting that operator. Let's do a curly brace. Do I have a quote open somewhere? I'm getting error on screen here. Okay. This looks correctly written. Got a couple of commas in there. Oh, well, you know what? I have no function body. That's a problem. All right. Are you all just sitting there laughing at me? Why didn't someone mention that? Okay. Let's define it this way. Ah, that's nice. So we could do the conventional rect area, say 3 by 4. And here we don't bother to name them because we're matching by argument order, and that gives the expected result. Here if we said 3 by 4 and oh, by the way, depth equals 2, then R would evaluate your function and say, I really don't care what depth is. That's an argument I don't know about. I'll let you pass it to me, but I'm not going to do anything with it. So you might ask yourself, what use is it to allow functions to accept arguments that they don't do anything with? Wouldn't it be better to tell the user that it's an unrecognized argument? Well, there are some very good reasons. I'll give just a couple. One is that the function you write may itself call other functions, and those functions may need those extra arguments. Your user, which might be you, by the way, may be trying to pass arguments not to your function, but to functions that your function calls. Now, that's a mouthful. The other reason is that the user, especially in plotting examples, and I think you may have encountered these in your lecture on plotting examples call, under the hood, those functions call lots of different things, and some functions use some arguments, some functions use other arguments. So even functions that don't need extra arguments may have to be prepared to handle them, just because users are taking the approach of supplying all arguments to all functions and letting the functions sort them out. Now that sounds wild and crazy. In a way it is. Languages like C++ don't allow you to do that at all, at least not at a basic level. But functions like R allow that. It's a powerful feature, but you'll need to deal with that because anything that's powerful also has dangers, and it's up to you to manage the danger of that. In this case, we can do some useful things with functions, and I'll give you an example here. We're going to write a function that not only calculates the area of a rectangle, excuse me, but also reports the units. And if we're going to report units, we're going to be getting specific. So we'll call this specific rect area. And hopefully you'll see now what I'm talking about with a live example. And here we're going to say this function accepts all comers, any arguments you want to pass. And it also accepts another argument called units. And these are units of length. And then we're going to say, we're talking about rectangles that have a default length. Default length is measured in meters. And we're going to try to, well, you know what? Let me write this in curly braces just to make it obvious what I'm doing. We're going to say paste. And now let's say, what are we pasting here? You know what? Let's say return value is paste. I'm breaking this up just a little bit more than usual. And I'm going to call rect area that we already wrote and supply it with our default arguments. You know what? Let's break that up even more. You can see a classic coding technique of expanding or collapsing your code as necessary to make things explicit or not. Let's just do this. So the very first thing we do is take all the past arguments except for units, and we pass them to rect area and get a result back. So then what we're going to do with that is paste units on the end. So return value is going to be paste area and units. Then we're going to go ahead and return the return value. Not terribly complex. This all could have been written as one-liner, but it's easier to read this way, I think. Oftentimes you may hurt even yourself who wrote the code by writing things that are shorter than necessary rather than the alternative where you spread it out like this and remind yourself exactly what each step is doing. Let's go ahead and define this and give it a couple of tries. All right, so now we could do something really wild and crazy. Let's just remind ourselves, what are the args for specific rect area? Let's see, we're going to need some dots and some units. Well, we don't need to supply units because those are default. In this case, we would have to go to the help for this function and figure out what those dots are supposed to contain. Unfortunately, I haven't written any help for this function, so you're just going to have to take my word for it or look at the function definition and see that the dots should be arguments appropriate for rect area as previously defined. So we know what rect area takes. We know it has a default height, and that it needs a width. So we'll just say specific rect area, and then we'll supply a width of 3. And we get back a result with a specific unit of measurement. Not just 9 somethings, but 9 meters. Now, it just occurred to me that units for area should be squared of something. So this should really be 9 square meters, not 9 meters. That would be unit appropriate for length. So accept the example for its architectural properties and not for its unit correctness in this case. But just for a variant of that, I'll show you that we can now use this wrapper function to our advantage by, say, working in some other measurement system. We could pass the same function call, but in this case supply units, specifically coercing them to be some other unit of measurement, like square dot feet. something creative like that. We will need to close the parentheses to get a result. Now we see 9 square feet instead of 9 meters as we expected. So you see the power of the ellipses here. The rect area function just took our width argument, passed it on to rect area, did what it was supposed to do with the units argument, and you get the combined power of both functions in your result. Any questions about that? Okay. I'm going to show you one other set of questions that is available to you as exercises. And this is also in the book that you'll be getting very soon. Check back on the website in a few minutes after class. We see in section 361 that number 1, we need to write a function to evaluate the quadratic formula, which you all have memorized, but I give it here anyway. And your function should ignore unexpected arguments, and by default it should return the additive root. So you have your option here, but you can supply a default. You'll also need to use the ellipses as we demonstrated in class. Number 2 says write a function to calculate area under the curve in terms of dose, clearance, and bioavailability. So you can assume bioavailability to be 1 if it's not given. And here's an equation of for dose as a function of clearance, bioavailability, and AUC. You'll have to rearrange that a bit, but it does give you a chance to try something in a pharmacometric context rather than just simple algebra. And you can ask a quick question about that if it's not clear. Number 3 says, suppose most of your data files are tab separated with headers and have dot to represent missing values. Write a wrapper function for a read table. That's a base R function. Write a wrapper function for a read table that sets these arguments so the caller only needs to supply a file name. Use the ellipses to let the caller set other arguments. Is the caller able to override your value for header? A goal of this question is that the answer be yes. You want the caller to be able to override your value of header. That gets a bit more involved, but I think you can do it with the examples, with what you learned from the examples given today. Also, you can look at the examples in the book chapter, which are substantially similar to what I demonstrated for you. In this chapter, we actually have only one more topic, and that's variable scope. You won't need that that topic for most of what you will be working on. I don't even think you need it for the additional exercises listed at the chapter end. You can get into those additional exercises on your own. I will certainly have time, I believe, to go over them on Friday with you. On Friday, we will spend the whole class period just going over this scope concept and then hashing through whatever remains to be explained of the exercises that are assigned in this chapter. Any questions? Okay, well that brings us to the top of the hour. We'll end the lecture here, and I'll also be watching for your questions and comments on the course website. Thanks for your attendance.